Okay, so I'm going to implement a GPU version of the self-collision implementation I've been working on. Currently a discrete self-collision implementation using particle-to-particle or point-to-point collisions. So I'll just show it quickly. So this is a basic example without the self-collisions, and then I turn them on, and you can see that some form of self-collision exists. It's not perfect. We get these planar areas here that clearly intersect because there's no point to triangle collision. That's something I'm working on. Should be using more of a continuous collision detection approach. But particle-to-particle collision detection is relatively simple in terms of the algorithm. It's got decent performance when used with acceleration structure, which we'll get into in a minute, and is worth having as an option, a cheaper option. So essentially, if we just go into Paint, I mean, I'm absolutely terrible at drawing, but we have some cloth manifold that's then represented by, particles at the vertices, and technically they would all have the same radius, but we can just imagine, we'll just draw two here for now, and and obviously these have constraints that go across them. This is like an edge constraint or a distance constraint, and the constraints are there to maintain the cloth length, the length between the particles, and we also need to account for when the cloth is going to fold over and self-collide with itself. And essentially the cloth is made out of triangles, and the vertices are the particles that the vertices of the triangles form the particles. So while these edge constraints are good at resolving the actual keeping the cloth like behaving like cloth because they're maintaining the distances, they don't resolve their actual self-intersection of the cloth from self-collision, and that's something that needs to be either resolved in a discrete or a continuous manner in terms of time integration, but then also or time stepping, but then also either from like a more of a continuous or discrete geometry implementation. And the discrete case for geometry's sake is dealing with the particles themselves and ignoring the surrounding surface that the particles themselves lay on. So I'll just try and. So, for example, let me try and think. I'm shit at drawing stuff. I'm trying to think of a good way to annotate what we want to do. The basic implementation is simple. We have two particles. Each particle is looping over every other particle that's near it, and is just within its same hash grid cell, which is the acceleration structure I'm using, because otherwise we would have the ON squared problem, where every particle has to check every other particle, which gets very, very expensive when you start having cloth that has more than 16 squared vertices in it, and essentially we want to check if the particles are intersecting, the radii are intersecting. We need to then push them out. We push both out, so this one would also be pushed out to make sure that they only touch but do not intersect. And that's essentially what this implements. There's lots of research in terms of the best way to deal with self-collisions in real-time situations, and this Chris Lewin paper from GDC 2018, I think, is really good, and this is a predictive contact approach using CCD, which I'm not implementing yet, but I plan to. So like I said, this is a discrete approach, so we're not actually looking ahead in the time step. So we're looking at the current state of the cloth, checking for intersections and resolving them directly, opposed to predicting collisions that may occur and trying to stop them by enforcing a constraint or a contact. So the CPU implementation is very simple. Let me just find it. So I have a bunch of, this code is a mess at the minute. This is not what's going to be finally shipped per se, or when I put this on GitHub. But so essentially we loop through the particles for some number of iterations. This is essentially a Gauss-Seidel style relaxation method because it has to be applied iteratively. I'll get back to that in a minute. So we get the current hash cell index of the particle, and we get each other particle, and we form particle pairs. So for the current particle, we look at all the other particles that is in the same hash grid cell as itself, and we check basically if the distance to the other particle is less than the particle radius times 2. So if you think about it, we have two particles here, and if their intersection distance is smaller than 2 times the radius, they must be intersecting, and we want to project them away from each other so that they are now sitting, so they're touching but not intersecting, and thus the center distance from two particles would be 2 times the radius. So that's essentially what this does. And we project them away from each other from the direction based on the previous positions, because if we use the positions after intersection, we can't guarantee that they're going to be projected away in the original direction that they headed, which will lead to the cloth getting tangled. So this is what this does. So this is very much based on Thomas Jacobson's work, which is also like a precursor to position-based dynamics. This essentially is position-based dynamics, but with some differences in the fact that we don't explicitly store velocities. We use velocity-less Verlet integration, and the velocities are implicitly derived from the integration and the storage of the previous and current position. So we don't actually work with modifying the velocities directly, which means we directly integrate position from acceleration, which has advantages and disadvantages. Means that we don't have to do 2 integration steps to integrate from acceleration to position, and possibly have oscillations and desync of the integration, as Thomas Jacobson showed in his original paper. However, the disadvantage is that we don't have explicit control over velocities. So everything we do is to either manipulate an acceleration, the forces, and then the accelerations from that, or we are directly manipulating the positions. So we have an initial integration step, which is the Verlet integration, as I said, based on some forces. But then everything after that, everything to resolve the collisions and the constraints, is done through direct position modification, or position projection, as is the correct term. So this is basically what we do here. We need to enforce Newton's third law. So we project both the current particle away along its original direction, and the other particle along its direction, so they now separate. And now one thing here you'll see is that we don't actually use square roots because they're too expensive. When you're doing this over lots of particles for multiple iterations for a single frame, I don't want to do a lot of square roots, so all the distances are in a squared basically. The only square root we do actually is to get the final intersection distance, but theoretically we could approximate this, but it's just easier to do one square root there. But the actual distance check here, you'll see, uses square distance, which is basically a Euclidean distance function without the square root. So therefore the particle radius we're checking is also squared, 2 times particle radius squared. So this is obviously single-threaded, it's not optimized, doesn't use SIMD instructions. Probably could be further optimized, even though it's relatively simple, but it has decent performance for now, and obviously a big part of that is the use of the hash grid. So the best reference for the hash grid is from this paper here, the Optimized Spatial Hashing for Collision Detection into Formal Objects. This is like the original reference paper. There's also where is it? Oh yeah, this one. Simon Green's NVIDIA, I think GTC paper, where they go over the same approach. Although originally, like them, I did use a uniform grid, but uniform grid is too slow because you have to do a gather step where you have to compute particle distances per cell index, which is too expensive. It's much cheaper to just use a hash approach where we implicitly have a uniform grid represented through a hash function, and we use the position of the particle as the key, and we return a single cell index for the resultant position. And we're basically doing that, so particles are spatially organized into cells that's stored in this hash grid class here, which essentially then just stores an array of an array of arrays. So it's actually an array of pointer arrays, because we don't want to store arrays for cells that actually haven't been used in the hash grid. So we only allocate cells in the hash grid that actually have particles in them. So the actual GPU implementation. So this is going to be done using compute shaders in Unreal Engine, and Unreal Engine doesn't give easy access to compute shaders in terms of the API, but it is there, and it's relatively not easy, but it's okay when you know what to do and you've done one. Because I'm going to be copying a lot of code from the previous implementations. I've actually already implemented my my constraint solve in compute here, which you can see, and also the Verlet integration itself, which is very easy to do because there's no data races, because you're basically just doing each particle integration separately. But with constraints, we have the problem that we're dealing with two particles at the same time, and each particle is running in its own thread, and we don't want to introduce data races into the mix, so we have to account for that. So this is enough exposition, I think. We need to just get into the actual implementation. I'm trying to think anything else I haven't covered. Like I said, this is the big difference between the single-threaded CPU version and the GPU multi-threaded version, is that we won't be using Gauss-Seidel style relaxation. We're using Jacobi, which is essentially very similar, apart from we don't directly inject the updated positions into the same iteration. We have two buffers. We have a scratch buffer and a current buffer, current particle position buffer, and we read from the last iteration and we write to the current iteration. We do not write back into the same iteration that we read from, because that would introduce a data race because of the multi-threaded nature. We can't guarantee that all particles all particle threads completing at the same time, and if we start writing back some particles iterations directly within our iteration before their iteration is finished calculating, they may read a value that's not based on their original state. It's kind of hard to explain, but basically Jacobi is like a multi-threaded friendly version of Gauss-Seidel, and I mean they both originate from relaxation-based methods of solving linear equations, linear systems equations, and this is essentially what this is. But opposed to building a global matrix and solving the inverse of that matrix, we're just doing localized relaxation directly per particle for particle pairs. So we need two buffers, one that we read from, one that we write to. The final one that we write to then becomes the one we read from in the next iteration, and so forth. They get swapped essentially. And I'll go over that. So we need to just get into it now. The biggest difference here as well is that we have a hash grid. For constraints, for the constraint solve, we didn't need a hash grid because I actually just stored each individual particle's constraints. The constraints are actually represented as a small struct, a small object, that also has a matching GPU implementation in compute. And we loop over the particles. We check the current particle and we integrate we project the constraint, accumulate the delta, and add it to the current particle only. And we're going to essentially do this here. We cannot add it to both particles because, again, we're modifying another particle that's not ourselves within our own thread, which will lead to a data race. The other approach is that you could store all the positions. We could evaluate both particles directly. I mean, we do evaluate both particles, but we don't store both particles. You could store both particles directly into a separate buffer and then have a thread synchronization, or in a completely separate compute shader, then apply the delta to both particles simultaneously as a separate compute shader operation. But obviously that introduces two separate compute shaders, or introduces synchronization, which causes slowdown. So essentially what we do is we evaluate the constraint as both particles, but we only actually add the delta to the current particle, and then this other particle will also evaluate the same constraint in its own thread and only add its delta. So it's essentially, it amounts to the same operation, but it's thread safe, and it means that we're not modifying particles that our own thread doesn't belong to, because essentially each thread is a single particle index, and threads map to particle indices. Yeah, okay. So let's get started. I've already done a bit of setup, so there's a few ways that we can actually pass the hash grid to the GPU. So we have the hash grid, and it's an array of arrays, like I say, where each inner array is each cell of the hash grid, and we have some number of cells. Max number of cells currently it's 1,000. So we could potentially have 1,000 cells allocated for the whole hash grid, which is unbounded technically. It defines the whole 3D real space of where the cloth lies. And each cell obviously contains particle indices to the particle array. So one of the typical approaches is that we actually sort and this is covered in Simon Green's paper here. I think it is. Oh yeah. So you can basically sort the particles into cell order, and then also have an offset array which defines where each cell starts. So for example, the particle indices, this is cell 0, and then it goes on from here. I think I'm reading that wrong, but essentially, yeah. Essentially, we have an array that is the sorted particles. So you sort them by cell index, and then a second array which stores the offset to the start of that cell index. And this is good because it means that we don't have to actually pass onto the GPU each cell's indices separately. But it means that we have to do a sorting operation on the host side, and then also pass a second array, which is just these offsets here. So it's actually efficient in memory, but it has got some overhead that we need to sort the particles each frame. And because the hash grid is not constant, it's per time step created, this would have to be done on each time step or each sub step. So not exactly mega efficient. However, because I don't really care about memory so much right now, I'm going to go with the approach where I actually pass the hash grid in a more direct way, where I'm actually going to pass it as an array of structs, because HLSL doesn't support an array of arrays. So I'm actually going to pass actually a buffer of structs of these cell index lists here, and each cell can have some max number of particles. This is going to have to be increased though, because I know for a fact that some cells are going to have more than 16. So let me just note this quickly. So each cell can maybe have, I don't know, 64 particles max. Oops. So we'll have max 64 particles. And we'll hard code this. So this isn't ideal, like I said, because we can't have an array of arrays. We have to have an array of structs. Sorry, an array of structs of arrays, although there's only a single array. So it's basically going to be an array of these cell index list types that then store an array of 64, a static array of 64 cell IDs, and these are the particle IDs of the cell. But because we might not have 64 particles in a cell, we also store the count, so we know when we're looping on the GPU how many particles we need to loop over. So I'm going to pause this and actually going to get into the coding.